So we're starting quadratic functions and their properties, and we're going to take a look at what a general quadratic function looks like, define some vocabulary words that go along with quadratic functions, and we're going to take a look at what the graph would look like. So we're starting off with the fact that all quadratics are in standard form when they meet this model right here. When I say f of x is equal to ax squared plus bx plus c, I'm saying we can fit every quadratic function into that model. Okay, so to start off, just as a reminder, remember that this notation here, f of x, is just function notation. It means the same as y equals ax squared plus bx plus c, but you're going to see a lot of this f of x, so I want to reintroduce it and let you see it again. And remember that f is not a variable, it just means the name of the function. We're saying this function is called f, and this is the variable that we're going to plug in for. So for example, if I did something like up here, f of 3, what I mean is go down here into this function called f, plug in a 3 into this space and into this space. Okay, so you're going to see some function notation showing up, so I just want to remind you about what that looks like. Okay, so here are some quick examples of things that are quadratic functions that will fit this model here. If I said, for example, f of x is equal to, and I just filled in letters here, and we saw this when we did quadratic formula and when we did factoring, AC factoring. We said that I could do something like 3x squared plus 4x minus 10, and I'd say my a value is 3, my b value is 4, my c value is negative 10. Okay, here's a second example. I could say g of x, I just changed the name of the function from f to g, which is fine, I can call it whatever letter I want. And I could say that, for example, x squared minus 25 also fits this. You might say, well, wait a second, this only has 2 and this has 3. Well, remember, sometimes these values will be 0, so I could say that this is similar to x squared plus 0x minus 25. And now it fits, right? My a value is 1, my b value is 0, which is why we don't see it in the simplified form. And my c value is negative 25, right? So any function that starts off that has highest exponent of x squared fits into this model, what we call standard form. Okay? So when we graph these functions and we take a look at the picture of what a function looks like, we're always going to get this U-shaped graph, right? So it doesn't matter. It might be really, really skinny and it might look something like this. Okay? It might be upside down and be really, really wide. Okay? But it doesn't matter what it how it's stretched out and compressed. It's always going to be a U-shape, and that U-shaped graph has a name. It's called a parabola. So we say that quadratic functions always graph to a parabola. Okay? And so again, we're going to see a bunch of these as we graph them. So the first important definition and first important idea when we're talking about quadratics is this idea of symmetry. So whenever we graph a U-shaped graph, when we graph a parabola, we say that this has symmetry. And what that means is that if I were to measure, take any point on this dotted line, which I'm calling the axis of symmetry, and if I were to measure how far it is over to the parabola, let's say, for example, this was 3 units, I know for sure that there's another point exactly 3 units on the other side. And that's what symmetry means. It means it's an exact identical match on the left side and the right side of that line. There could be another one down here. I could say maybe if I measured this, this is 1 unit away from the parabola. If I measured on the other side, I know that there's going to be another point that's also 1 unit away. Right, so this axis of symmetry is the name of that dotted line, vertical dotted line, that I can write down the middle of the graph that's going to give me an exact mirror on both sides. And we actually saw this already. If you take a look at absolute value we talked about way back in the beginning of the year, that's also true. I can draw a dotted line down the middle of that. I can draw, if I put a point, for example, 1 unit to the right, I know there's also another point 1 unit to the left. And that's going to help us out. We're going to use that to save ourselves some calculations when we're trying to get a nice shape for this graph. Okay? So here's your second definition. We're going to say that the point where the parabola turns around, which we could call a minimum or a maximum, right? We're going to say this graph's kind of going down and then it hits some point, which we're going to call the vertex, and then it starts heading back up towards the top of the graph again. So we're saying that turning point, that lowest point on the graph, in this case, we're going to say is called the vertex. So a vertex could be a highest point. My graph looked like this, which it's going to look like this sometimes. I'd say that point right there is now a maximum. It's the highest point. If I asked you to name for me a point higher than this, you couldn't name a higher one, right? There's nothing up here that's higher than that. And if it happens to be our normal regular shape U, I'd say that it has a minimum. So depending on whether it's upside down or right side up, I may call the vertex a maximum, I may call it a minimum, and we'll see how to flip that graph upside down and how we'll know whether it has a maximum or whether it has a minimum. Okay, so if I give you a simple problem like this and say, let's identify the vertex, I can look at this graph and I can say, all right, this is a parabola, it is a quadratic function, and if I go to this point right here, okay, that is where the graph turns around and starts heading back up, and I would say that that looks like the point 1, negative 1. All right, so that's what the vertex is. It's that point. And then it says, is this a maximum or is it a minimum? Well, I'd say, well, this has the lowest point, right? There's no point that is lower than this one. So I'd say in this case, it looks like I have a minimum. Okay. And then in letter B, it's the opposite. I have a highest point on this graph. There's nothing higher than the vertex, which it looks like in this case is 0, 3. Okay. And I'd call that one a maximum. Okay, so we can have minimums or maximums, but in both cases, those points are vertex. Right? This is a vertex. This is a vertex. It's just whether it's high or whether it's low. Okay. So now that we know those things, let's graph one of these and see what it looks like, and see why we want to know about these important points. Okay. So if I give you this function, and I'm saying this is a quadratic function, and I say let's graph this, one way that we can do that is we can just make an XY table. And XY tables work for any type of graph. So I'm going to just choose some points and I'm going to plug in and we're going to figure out what comes out. So I'm going to start off and I'm going to say let's do -2, -1, 0, 1, and 2, and let's graph that. So if I plug in -2 here, -2 squared is 4, and half of 4 gives me a 2. So that's a point. -2 up to 2, that's a point. Okay? And I can keep doing that. I can say -1 squared. Well, that's 1, and half of 1 is half. So it looks like I have a point here at -1, and then at a half. That's a point. Right? When I plug in 0, I get 0 squared, which is 0, and half of 0 is still 0. So it looks like I have a point right there. And I can keep going, and I'll let you plug in the rest of them, but what you end up getting is a half and another 2 out. And this is what our final graph is going to look like. Right, so I would say this right here is my graph. And if you notice, I get the bottom of a nice U shape. So if I were to complete this, I would say you're going to get something that looks like this. Right, so there's my U shape. So if you notice, this is a parabola, just like we thought it was going to be. All of these functions are going to look like parabolas. Right? It does have a lowest point, so I'd say 0, 0 is my vertex. And it looks like the y-axis is that axis of symmetry line that's cutting this right now. Okay, so here's your last question for this video anyway. If I asked you what is the domain of this function, okay, this is something you're going to see keep coming up, the domain and the range. The domain of this function is basically saying, well, what numbers could I input into this graph, and what parts of the x-axis are going to be covered when I do that? So if you think about the function, and I say, well, what could I plug into that and get something back? Well, I can plug in positive numbers, and I can square positive numbers. I can plug in negative numbers. We did that right here. I plugged in negative numbers. I could plug in fractions and square fractions. Right? So there's really not a whole lot of restriction on what I'm allowed to plug in that's going to give me something back. So we're going to actually say that the domain in this case is all real numbers, or and this symbol right here means all real numbers. This is really saying we're allowed to plug in anything that we want. Right? And that makes sense when I look at the graph, because this thing is getting wider forever this way. Right? This is going to keep going that way. This is going to keep going that way. And it looks like I'm going to cover this entire x-axis. I can say way over here there's a point, right? Here there's a point. Here there's a point. On the other side I have points. So it looks like I could go up from anywhere I wanted on the x-axis, and I'm going to be able to hit this parabola because it's going to keep getting wide. Okay? If I tried to do that with the y-axis though, and said, can I keep going left and right and hit the graph? Well, it looks like up here, if I started it on the y-axis and I look to the left and the right, I'm finding lots of graph here. But if I go down here, there isn't any graph. So it looks like when I'm talking about range, there's a bunch of parts of the y-axis that do not ever come in contact with the graph when I try to move over. So I'm going to say I can only use the y values that are greater than or equal to 0. Right? Y is 1, and y is 2, and y is 3, and y is 4. These points all have graph next to them. But if I go down to the negatives, I don't have a graph. So I would say in this case, my parabola has a range that is only the y values greater than or equal to 0. Okay? And so you'll see some more examples of using domain and range.